Hey guys, welcome back to another video. In this video, we're going to solve a few hard questions from organic chemistry from A2 level chemistry. I've sorted a few questions out and we are going to start from this question 1, that is from winter 22, paper 4.1, and this is question 7 of that paper, and it's saying the structure of compound P is shown in figure 7.1. Now this is a benzene structure, and then you have an extended structure of amine group attached, and this is your ester linkage. This is what? An ester linkage, double bond O and O over here, right? So C bonded to O and bonded to another O and another C over here. So this is an ester. Now they're saying that P is optically active. Use an asterisk to identify all chiral carbons atoms on the structure of P in figure 7.1. So they're asking you to find the chiral carbon in this P structure. So very simply, you're going to see that over here where the benzene structure exists, there's not going to be any chiral carbon. Why? Because all of these carbon atoms are sp2 hybridized. So these are not going to be your chiral carbons. Keep that in mind. This has 2 hydrogen atom, not chiral. This has 4 groups. N, carbon, another group of carbon, and H over here. Hence, this is your chiral carbon, right? Hence, it is optically active. There are no other chiral carbons. This has 3H. This has double bond feature, sp2. So yeah, 1 chiral center. Now, second question, plain polarized light is passed through a pure sample of 1 enantiomer of P. This is then repeated with a pure sample of the other enantiomer of P. Okay. Describe the results of these two experiments, stating the similarities and differences of the results. So they're passing a light through 2 types of enantiomers, like the same thing, but 2 enantiomers. That is, one will rotate light clockwise, the other will rotate light anti-clockwise. So since it is optically active, it will have 2 optical isomers. So both the isomers will behave differently. Now, usually we don't see too many questions coming from your enantiomer chirality chapter, but in general, it is just about being able to rotate your light. That is all it talks about. So there are some rock features, that is when you have only one sort of enantiomer present in the entire mixture, they tend to be better or more effective drug, since there is only one type of enantiomer present, and it is more effective since it is not contaminated by the other enantiomer. So the effect will then decrease. It will be less effective. So that is all about chirality and enantiomers. So in this case, they're asking you what is the difference if I throw some light on the 2 different enantiomers. So polarized light is rotated in equal amounts in opposite direction for both, right? So for both the enantiomers, the magnitude by which the light rotates stays the same, because both are the same compound, just optical isomers of each other. Hence, the direction of rotation changes, however, magnitude doesn't change. That's it. Part B, this compound P can be used to make compound Q in a single step reaction. What is Q? So Q is benzene structure added to your amine group, this amine group, where one of the H has been substituted, mind you, one of the H has been substituted to bring in this structure. And on the other hand, you still have your double bonded O, and you have this as well. So this part has not changed. However, over here, substituting one H atom, you have this carbonyl group, ketone group, right, attached to it. Fair enough. So give the structural formula of the compound that is added to P to make Q, and give the formula of the other product of this reaction. So what has been added over here? We have added CH3, or if I break it down, CH3, C, double bonded to O, Cl. So what you see over here is a ketone group, right? A ketone group. Now to be able to put this structure, notice there is a CH3 over here. That is this carbon atom bonded to three hydrogen atoms, and this carbon atom bonded to your oxygen atom. And this Cl, mind you, will react with one of the H, or if I show you over here, so if this has two H over here, one of the H will react with Cl and leave the structure. I mean, react as in it will be eliminated. So it's sort of a condensation reaction. Right? So your H and Cl is eliminated, and this C will now form a bond with this nitrogen atom, right? So this C forms a bond with the nitrogen atom, H, and Cl has been eliminated from the structure. Fair enough. So this structure has been added into the structure by substituting the hydrogen atom. Fair enough. Now the byproduct again is going to be what? HCl. Fair enough. So that part was very simple. You're going to bring in this ethanol chloride, and there's going to be reaction where the H is going to be substituted by putting in CH3CO+. Okay? So H will be substituted and you put in this structure and you form this ketone structure. Now for part 2, they're telling you an ester is treated with lithium aluminum hydride in dry ether. The ester linkage is cleaved by the addition of 4 hydrogen atoms and 2 alcohols are produced. Draw the structures of the compounds formed when Q is treated with an excess of lithium aluminum hydride in dry ether. So they're telling you your compound Q, they're treating it with reducing agent, lithium aluminum hydride. Now they're also telling you this ester linkage, notice, this ester linkage is being treated by a reducing agent and hence it will be broken off, right? So the ester linkage will be broken off. And they're telling you ultimately, after reducing this compound Q, 2 alcohols will be produced. Fair enough. And while breaking this structure, while cleaving this structure, 4 hydrogen atoms will be added over here. So let's see what compound is formed. The first thing is going to be this, where you have CH3, H, right? CH3 bonded to O. This part is broken off to form what? To form an alcohol, right? And it's going to be CH3 bonded to OH, right? And that, my friend, this H is going to be your first H that has been added to the structure. The first H that has been added to the structure. They mentioned 4 H should be added when breaking this ester bond. Now let's see. The first one has been added. Now over here, what's going to happen is when breaking this structure, this carbon atom, notice this carbon atom will gain a hydrogen atom, since this bond is broken, right? So this bond will be broken, and 1 hydrogen atom will be attached. Consider this the second hydrogen atom attached. Next thing. Notice another thing, that ketones can be reduced into alcohols. So they'll be reduced into 2-degree alcohols, right? Yeah, they'll be reduced into 2-degree alcohols. So since you're using reducing agent, the ketone part of the molecule will also get reduced. So this double bond will be broken off, and what's going to happen? This oxygen gains what? A hydrogen. This hydrogen. Consider this your third hydrogen atom added to the structure. Next thing. If this double bond is broken, carbon is only making 1, 2, 3 bonds. So 1 more hydrogen atom will also be added to the carbon atom. and that is going to be your this fourth hydrogen atom, making how many? 4 hydrogen atom in total. So you have ultimately added how many hydrogen atoms? 4, while cleaving this bond, right? So I know this is one of the alcohol produced, that is methanol, and the other one is this entire structure. This entire structure is going to be another alcohol, where this acts as our alcohol. This OH, this third hydrogen atom, acts as our alcohol, right? Fair enough. So this is now, it is going to be for a 1 degree alcohol, since one carbon atom, R group attached to this carbon atom, right? So over here there is one hydrogen and R group, and attached to OH functional group. So that is first degree alcohol. Anyways, so we are going to draw this as our another alcohol in addition to our methanol that got cleaved from the structure. Now another thing, notice this double bonded O is missing from the structure. What happened to this? What happened to this? This is also a ketone. This is also what? A ketone. Hence, this is going to be reduced to another alcohol. This is going to be your second degree alcohol, since 2 R groups, right? Fair enough. And one hydrogen atom will be attached over here, and one hydrogen atom attached over here, right? This doesn't fall under your 4 hydrogen atoms attached, since these are other than the cleaving part of the structure, right? They had mentioned that when cleaving the bond, 4 hydrogen atoms will be attached. So this is apart from that. So this double bond broken, 1 hydrogen added, another hydrogen added over here. Hence, how many hydrogen added? 2 hydrogen added, forming a second degree alcohol. Fair enough. So these are going to be your ultimate products. Now, one would usually forget about reducing this part, right? Okay. Now, part 3 is going to be what? Part 3 is going to be compare the relative basicities of compound P, compound Q, and phenylamine. This is your typical phenylamine, and they're asking you to compare. Oh, this is not Q, sorry. Q, and P, which is a better base. So for being a better base, you need higher density on the nitrogen atom, higher density of electrons on the nitrogen atom to be able to pull electrons, right? Now, in case of Q, where is your nitrogen atom? In case of Q, this is your nitrogen atom. Now, notice one thing. This nitrogen atom is closely connected to your oxygen atom, which is what? Highly electronegative. And the worst part is, there's also a double bond over here. Now, let's look at P. This P in this nitrogen atom is bonded to this R group. R group is bonded to another carbon over here, and then this carbon is bonded to the double bond. Whereas in case of Q, N is bonded to this carbon atom, and this carbon atom is bonded to the double bonded O, right? Fair enough. In case of this is bonded to one carbon atom, and then this carbon atom is bonded to another carbon atom, which is forming a double bond with your O. Great. Now, in case of phenylamine, this phenylamine, again, the issue with this is it is losing some of its electrons into the ring structure. However, there is no such, double bonded O or highly electronegative atom over here. Although the electron density is lost into the structure, still it does have higher amount of electron density. So now I'm going to say that Q is going to be the least basic. Phenylamine is going to be a bit more basic, and P is going to be most basic. Now, why you ask? Notice. In case of P, there is a carbon atom over here, right? There is a carbon atom over here, chiral carbon, and there is a long chain of carbon atoms over here, which is going to have an electron donating effect. Now notice, your Q has a lone pair of electrons on the nitrogen, delocalized into the carbon-oxygen double bond. Now, in case of Q, this nitrogen directly bonded to a carbon, which is directly bonded to oxygen with a double bond, right? So the lone pair over here is being lost into this double bond. While in case of phenylamine, these electrons are delocalized into the ring. While in P, the alkyl group that I mentioned over here, this R group is going to have an electron donating effect, this specifically. So 1, 2, right? 3. These carbon atoms are going to have an electron donating effect. Fair enough. So while in P, the alkyl group has an electron donating effect. Therefore, nitrogen will have a more electron dense environment, which is why it is able to pull the H plus ions better, right? It is able to pull the H plus ions better. Fair enough. Now, the N in P, right? The N in P has the greatest ability to attract the proton. So, due to the electron donating group, it has the greatest ability to pull the H plus ion. In case of Q, notice it is being lost into this strong electronegative atom, while there is also a double bond over here. So, the electron density on the nitrogen is very low. While over here, it is losing electrons. However, it is going into the ring, which is why the lack of electron density is not that high. It is relatively higher. I mean, the electron density is relatively higher in comparison to Q, which is why compared to Q, it is a better base, and compared to P, it is a worse base, since in case of P, the advantage is electron donating groups. So that is your part 3. Now part C is going to be, P can be used to make compound R in a two-step reaction shown in 7.2. So what is R? R is going to be, what has changed? So these are the same as it is, and the NH2 group has been added. Okay, so they tell you this can be done in 2 steps. Very simple. You will nitrate the benzene structure, add NO2 group, then reduce that, hence making amine. So identify the reagents and conditions used to for the 2-step reaction. You're going to nitrate, that is HNO3 concentrated, H2SO4 concentrated, temperature between 25 degrees Celsius and 60 degrees Celsius. And you're going to nitrate the structure. Now, in step 2, you're going to form phenylamine by which ester bond? Oh, right. So the change over here is also this this ester bond has been broken. So a carboxylic group COOH has been formed over here. So apart from the NO2 group, so there was, after step 1, there's going to be NO2 group over here, that is NO2, right? NO2. So after the NO2 group has been attached in step 1, in step 2, this is going to be reduced, right? This is going to be reduced into NH2, right? Now the other thing is you also have to break this structure, that is the ester bond, to form your COOH, that is your carboxylic group, and this part is going to leave, that is CH3OH. Your methanol is going to leave the structure. So in step 2, you're going to say you're going to form phenylamine plus you're going to break the ester bond. So this part, that is tin and concentrated HCl, is going to reduce your nitro group, and you're also going to add NaOH and reflux the structure such that you can break this ester bond, right? You can go through anything, NaOH or acidic reflux, both are going to work. Even in acidic conditions, you'll be able to break. So in both acidic and alkaline conditions, you'll be able to hydrolyze the structure, that is break the ester bond, right? So even in this case, you can break the ester bond. Fair enough. So step 1, you're nitrating, and step 2, you're reducing the nitro group, and you're also breaking the ester bond such that you create this carboxylic group, and the methanol group takes an exit from the structure. Fair enough. Now, second part, C2, I guess. Complete table 7.1 by drawing the structures of the organic products formed when R is treated separately with the reagents given. So R, where is my R? So this R is treated with different reagents such that it will form certain products. So this R is going to be treated with first HNO2 at cold conditions. Now HNO2 not HNO3. This is going to in cold conditions, this is going to form the diazo group. That is, it's going to form this ion, that is diazonium chloride. If you did it in the presence of HCl, since they didn't mention HCl, you can say diazonium ion, right? So it's going to form diazonium ion in cold conditions, 0 to 10 degrees Celsius, and in addition of HNO2. Fair enough. So what's going to happen is this structure is going to stay as it is. Basically, you're going to add N over here. You're going to add N over here. This H2 is going to take an exit, and you're going to add an N over here, form a triple bond, giving a positive charge over on this nitrogen atom, since this nitrogen atom is forming 3 bonds. 3 with this nitrogen atom, and 1 with the benzene structure, hence 4 bonds, So due to 4 bonds, it is going to have a positive charge, because usually what happens is nitrogen forms 3 bonds, right? 3 bonds, and it has a lone pair of electrons. Now over here, due to 4 bonds being formed, it is going to have one of its lone pair of electron being used to form the bond, hence 4 bonds and the positive charge. So this is your diazonium ion being formed in presence of HNO2 and cold conditions. Now the next one is excess bromine aqueous at room temperature. Okay, so room temperature bromine. Now NH2 has an electron donating effect, hence it's going to activate 2 position and 6th position, and this position is occupied, so nothing is going to happen over here. Hence what's going to happen is Br group is going to be attached in 6th and 2nd position. Fair enough. That is your question 1, a pretty lengthy one. Oh, there is one left as well. So part D of the same question, P can be used to produce compound T. In aqueous solution, T has a property called isoelectric point. Explain what is meant by isoelectric point. Very simple. pH when the species is a zwitterion as the dominant form. So basically, it is the pH at which this any compound, any, let's say even amino acids, are going to exist as zwitterions, or it is going to have a net charge of 0, while there is going to be one with COO minus, the other will have NH3 plus. So there is an exchange of proton, that is intramolecular exchange of proton, giving it a rise of charge on either side. That is one positive, one negative, but ultimately the structure is going to be neutral. Fair enough. Now, pH when the species is a zwitterion is a dominant form. Fair enough. So this is how you're going to answer question part 1. Now part 2 is asking you, T can polymerize under suitable conditions. No other monomer is involved in this reaction. Draw a section of the polymer chain formed that includes 3 T monomers. Identify the repeat unit on your diagram. Okay, so it is going to polymerize, and this is going to go through polymerization. Yeah, it's going to go through polymerization, and the only monomer used over here is T. Fair enough. So this COH group is going to react with this group, that is, this is basic group, this is acidic group, one of the H, and this OH is going to take an exit, forming H2O, right? And the bond is going to be formed. So if I draw this vertically like this, you're going to have one this, one this, one this, one this, and this carbon atom, this carbon atom, this carbon atom bonded to NH2, 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 and also your acid group, that is this carbon atom bonded to the O and OH. This carbon atom bonded to O and the OH. What happened to OH? OH and the H of N reacted together, formed water together and took an exit for making it a condensation reaction. Fair enough. So you're going to form this peptide link, that is amide linkage, whatever you want to call it, and this is going to continue over on this side as well, where this, notice, N is bonded to a carbon and this carbon is bonded to this benzene structure, and again repeat this, C double bonded to O, right? And this OH is going to be eliminated and is going to add with the nitrogen, be eliminated, and another amide linkage formed or peptide linkage formed, and you're going to repeat this structure once again since they want 3 monomers, right? So you're going to repeat this structure, try it yourself, see if you can draw the polymer correctly. Basically, H of NH is out of the structure, OH of carboxylic acid is out of the structure, forms a bond, and this is going to be amide linkage. So that is your polymerization reaction, and that is your question 1 of this video. Pretty lengthy. Now next one, question 2 is telling you tyrosine and lysine shown in figure 9.1 are naturally occurring amino acids found in protein. Isoelectric point is 9.47. Draw the structure of lysine, state in pH boxes below. So basically tyrosine, it has what isoelectric bond? Oh no, they're asking for lysine. So lysine has this structure, and in pH 7 its isoelectric point is 9.47. Now pH 7 is what? More acidic compared to 9.47. Hence, if it is more acidic, what's going to happen? It's going to gain H, right? It's going to gain H. Now the thing is, over here it's only going to gain 1 H, by the way. It's going to gain 1 H over here, right? NH3. Now the other thing is, for the lysine at 9.47, it is going to be NH3 and O minus. And at the pH of 12, what's going to happen? It is going to lose this H. It is going to lose this H and form minus. Nothing else. This NH2 group stays as it is. So that is your 9 part A. Now for part B, when ethanoic acid is treated with PCl5, product D is formed. When D is added to tyrosine, 2 different isomeric products E and F are formed. E has an ester linkage, F does not. Draw the structures of D, E and F in the boxes. So PCl5 added to ethanoic acid. So it's going to form ethanol chloride. Yeah, it's going to form ethanol chloride. You have your ethanoic acid, PCl5. So yes, it's going to form POCl3, HCl, and ethanol chloride. So ethanol chloride is going to be your structure D. And next, they're telling you that when this D is added to tyrosine, where is tyrosine? Okay, so this. When D is added to tyrosine, what happens is it is going to form 2 different isomeric products. E and F are formed. So now when you add this CH3, C bonded to double bonded to O and Cl. Now when you react this with tyrosine, what's going to happen is it can react with 2 groups over here. Right? Now, what are the 2 groups going to be? Ethanol chloride acts as a sort of acid, right? it is similar to carboxylic acid. And we say ethanol chloride or acyl chlorides are better or more reactive compared to carboxylic acid. Now, over here, what are the basic groups over here or alkaline groups over here, or pH greater than 7, whatever you want to say? It is going to be NH2. This acts as a base. Now, the other thing over here is your OH is going to act as your acid, right? It is going to act as your acid. Now, in general, what we see before, if you've seen the crash course or not, if you've studied it in general, that carboxylic acids reacting with your alcohols will form ester linkage, right? Now, even in case of ethanol chloride, since it is more reactive, acts similar to carboxylic acid. If it reacts with alcohols or amine groups, it's going to form either ester linkage or amide group, right? So similar to that, over here what's going to happen, this Cl is going to take this H part out, form HCl, and there's going to be an ester bond between this and this, right? So that's exactly what we see. C double bonded to O, and then added to O over here of the phenoxide, and HCl takes an exit, right? Fair enough. So basically it's, if I'm not wrong, nucleophilic addition elimination reaction. So HCl, it is a condensation reaction. So HCl is going to be a byproduct of this reaction. Now, for part F, that is the other way this reaction could have taken is forming amide. Basically this is your amide linkage. So this H can also take part in the reaction. H, C double bonded to O, Cl, H. CH3. So this H and Cl is going to be a byproduct, HCl, and this is going to bond with, this C is going to bond with this nitrogen atom, okay? Hence, ultimately you're going to have a amide linkage. This is your tyrosine, where this N had one hydrogen atom and this C had one Cl atom. These are going to form HCl and take an exit. Fair enough. So that is your part B. Part C, notice, complete table 9.1 by drawing the structure of the organic product formed when tyrosine reacts with each named reagent. Ignore the directing effect of blah 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 substituent. So okay. So when you add excess Br2 to, what are we talking about, by the way? Tyrosine, yeah. So tyrosine, this is your tyrosine. When you add, this is my tyrosine, right? Yeah. So when you add Br aqueous to it, you know Br is going to substitute the hydrogen atoms at certain positions. Now OH has directing effect of 2, 4 and 6. 6 position is occupied, and they told you this, not to consider this, not to consider the directing effect of this group. So it's going to occupy this 2 position and 4 position. Now, next part, an excess of NaOH is added. What's going to happen? If you remember from the video, that if you add NaOH to phenols, it's going to create phenoxide ion. Hence, it is going to form phenoxide ion over here. And the other thing is going to that's going to happen is carboxylic acid group reacts with what? NaOH. Hence, it's going to form this carboxylate ion, V double bonded to O minus, right? And you could also add Na plus, if I'm not wrong. I don't remember the maximum, but I guess you can also add the Na plus over here. That's not going to be wrong. Now, an excess of HNO3, nitric acid is added to the group. And what's going to happen over here, since you're adding acidic conditions, excess of HNO3, you're going to nitrate the structure, that is NO2, and you're also going to have H plus added to this N, right? Since it is acidic condition, the base or NH2 part of the molecule will take in one hydrogen atom. Now you may be confused that why, without the existence of H2SO4, that is, since H2SO4 reacts with HNO3 to form nitronium ion, and that nitronium ion then substitutes the hydrogen atom. So without the presence of H2SO4, how can the reaction take place? So basically, even if you don't have H2SO4 sometimes, this is going to dissolve in the solution to form nitronium ion. Since it is in excess, there is going to be some amounts of nitronium ion in the mixture, which will carry out the substitution reaction, that is with the H plus ion. So that is why you're going to have nitro group added, and also H plus added to your amine group, that is the basic part of the reaction. Okay, that is your question 2. Now for question 3, this is from Winter 22 paper 4.1, and some part C is telling you that chlorobenzene, that is chlorobenzene Cl, and chloroethene CH3CH2Cl have different reactivities in nucleophilic substitution reactions. Identify a suitable reagent to illustrate this difference in reactivity. Okay, the reagent chosen should give visibly different results with chlorobenzene and chloroethane. Now, in general, you know that chlorobenzenes are very strongly bonded. That is, the Cl atom is very strongly bonded to the benzene structure due to the p orbital overlap, which is why these are very unreactive. However, in case of, let's say, what do you call this, chloroethane, in case of chloroethane, substitution reactions can take place. That is, let's say, in case of NaOH, ethanolic NaOH, if you add ethanolic NaOH to the reaction mixture, what's going to happen? This Cl will be substituted by what? OH, right? Similarly, if you had added, I guess, NH3 in pressure and added pressure, ethanolic NH3 and add pressure to it, your NH2 would substitute this Cl. Similarly, you could do a couple of other things. You could also add Cn in the presence of KCN, HCN and KCN, or NaCN, and ethanolic conditions, and then reflux, I guess, I don't remember. And you're going to go through nucleophilic substitution as well. So you can do a bunch of things, right, to go through substitution reactions in case of halides. So the point is, how do you understand over here the difference between chlorobenzene and chloroethane? What you can do is, first, the main point is you have to identify the presence of chlorine in case of chloroethane. Now, you cannot identify the presence of chlorine in case of chlorobenzene, since this chlorine won't react with anything. However, in this case, this chlorine can be substituted and form AgCl and form AgCl, right? AgCl3, sorry. AgCl3, it is supposed to be AgCl only, sorry. Yeah, AgCl. So it's supposed to form AgCl, which is going to give you a precipitate, right? And to be able to do that, you will have to first go through ethanolic NaOH added to this mixture, such that this Cl is substituted by OH, and you're going to form ethanol. And then the substituted chloride ion will react with Ag plus, forming what? AgCl. And this is then going to give you your precipitate. So that is exactly what I've explained over here. However, over here, if you want to add, you can add ethanolic NaOH. Right. So you can mention ethanolic NaOH and say the reagent is going to be NgNO3. And then in case of, write the equation to describe the reactions that occur. In case of this question, you're going to provide the step-by-step process of this chloroethane reacting with NaOH, forming the alcohol and salt. And this salt reacting with AgNO3, forming AgCl and NaNO3. This is one thing you can do. The other is less complicated, and just say that the reagent is AgNO3 And this AgNO3 will react with the chloride ion, or this Ag plus will react with the chloride ion, forming AgCl. Simple, nothing else. And mention that no reaction takes place in case of chlorobenzene. So you can also do this. You can say AgNO3 is going to be the reagent, and the Cl minus reacts with H plus, forming AgCl, which is the precipitate. You can do either. Up to you. But yeah, this was quite tricky if you have to understand the substitution between chloride and OH ions, right? The nucleophilic substitution. That is why I mentioned a couple of times that you have to know the AS syllabus, right? You have to know the AS syllabus. Otherwise, being able to solve a lot of these small questions will be very difficult, because you need the idea, let's say from elimination reaction, you need the idea of hydrolysis, different hydrolysis, and addition of CN through what? Nucleophilic substitution and all that stuff. You need to have AS knowledge to be able to answer a lot of these questions. Now, part 3, explain the difference in reactivities of chlorobenzene and chloroethane in nucleophilic substitution reactions. So, you're going to say p orbital of chlorine atom is going to overlap with benzene ring, forming partial double bond feature, and this carbon-chlorine bond is very difficult to break, right? Which is why chlorobenzene are far less reactive. Fair enough, that is your question 3. Now moving on. Now for question 4, they're telling you isocyanic acid HNCO can form cyanuric acid C3H3N3O3 under certain conditions. Now this has a cyclic structure containing alternating carbon and nitrogen atoms in the ring system. So basically they're telling you that in the ring system, that is the cyclic structure, similar to cyclohexane, it is going to have 2 atoms repeating thrice. That is going to be the C and N bond. The carbon and nitrogen bond are going to repeat itself. Notice there are a total of 4 bonds. Now to have 6 atoms, you need only 2 of the atoms repeating itself. And in this case, they've told you nitrogen and carbon are going to be the atoms. So, they're going to repeat nitrogen and carbon over here. It is nitrogen, carbon, double bond, carbon, nitrogen, double bond, carbon, nitrogen, double bonds. Now, how do I know they have double bonds, by the way? Because this structure, you cannot make this structure without having CN double bond and oxygen and carbon double bond, right? So you know that there's going to be a double bond between the carbon and nitrogen and oxygen and carbon. Now you also know that nitrogen and carbon are both sp2 hybridized, which is why both of those can form the double bonds, right? So in this case, notice if I add all of these up and form the cyclic structure, notice the carbon atom has 5 bonds. 1, 2, 3, 4, 5. So it cannot have 5 bonds over here, because carbon at max, it is always supposed to have 4 bonds, which is why this double bond will be broken into single bonds. Hence this cyclic structure is achieved, right? And that is it for question 4. You're adding the 3 molecules, 3 of these up, you're breaking the double bond and forming the cyclic structure, right? Then these are going to be out of the benzene ring, since they've mentioned carbon and nitrogen atoms are going to alternate throughout the ring. Fair enough, question 4. And semi-last question of this video is question 5. This is from March 23, paper 4 to what is this? 2-lo-buterol is produced from Q as shown in figure 5.5. Q is this structure, okay, and it's going to go through 2 steps and form 2-lo-buterol, whatever that is. So basically what they've done is added CH3 NH2 over here, right? The Cl and one of the H got eliminated from the structure. right? Fair enough. So let's see what the question is asking. Suggest reagents and conditions for steps 3 and 4. Draw the structure of Z in the box. Step 3, what should happen? Step 3, you're going to substitute this CH3, CNH2. Oh, in the middle there is supposed to be a C, sorry. Because this carbon atom, sorry. So CH3, CNH2. So you're going to add that. You're going to add that to the Q. And H and Cl is going to leave the structure, forming this bond. Forming this amine bond. Fair enough. And that is step 3. So after step 3, you have formed this. You have formed this. Now in step 4, you're going to reduce this oxygen double bonded to the carbon to form the OH, form the alcohol, 2-degree alcohol, right? So you're going to reduce it via lithium aluminum hydride. Okay. Now in case of Z, what is Z? Draw the structure of Z in the box. Oh, basically this, as mentioned, it is going to have a double bond over here. It's going to have a double bond over here as per this, and only the Cl atom is leaving the structure along with one of the hydrogen atoms. Fair enough. E, the synthesis produces 2 enantiomers of tolubuterol. Define enantiomers. Enantiomers rotate plane polarized light in the opposite direction. And part 2 suggests one disadvantage of producing 2 enantiomers in this synthesis. So basically, if you produce 2 enantiomers, you need to separate them, and if you keep 2 enantiomers, they're going to be less effective. Okay, part 3 suggests a method of adapting the synthesis to produce single enantiomer. Not needed. You can use chiral catalyst or an enzyme. Okay, question 6. This is from 9701 summer 20 paper 43. This is asking you 3 tests were carried out on separate samples of organic acids shown in the table. The following results were obtained. So they're reacting methanoic acid, ethane dioic acid. Oh no, what is this? Wait, so let me draw this. CH3, C double bonded to O, C double bonded to O, OH. So there's a ketone group over here, and you have your carboxylic group over here, right? So it's acting as a carboxylic acid. And also a ketone group over here, carbonyl group. And you have your ethane dioic acid. Now they're asking you to identify reagents such that these reagents will only react with this or this or this and this, right? Fair enough. So for the first one, test 1, the reagents are only reacting with methanoic acid but not reacting with your ketone group or dioic acid. Now, in A2, what you've studied is 2 particular acids go through carboxylic acid, go through further oxidation. And those 2 are methanoic acid and ethane dioic acid. So in case of methanoic acid, what's going to happen is it only needs mild oxidizing agent to be oxidized. In case of ethane dioic acid, it needs a strong oxidizing agent. Now, in case of methanoic acid, you're going to add Tollens reagent or Fehling solution. Both are going to give you 2 different results. In case of Tollens reagent, you're going to form silver mirror. In case of Fehling solution, it's going to give you brick red PPT. And so your methanoic acid is going to be oxidized, and it's not going to react with any of these, that is carbonyl group and carboxylic acid or ethane dioic acid, none of those, because it's a mild oxidizing agent. Next, part 2, they're telling you it doesn't react with methanoic acid. It doesn't also react with ethane dioic acid. It only reacts with this group, which has a carbonyl group. That's the only difference. Now, this has nothing to do with further oxidation of carboxylic acid. So identify what's different about this group in comparison to these 2. The only main difference is carbonyl group added over here. That's the difference. So this carbonyl group you can identify how? You can identify using either DNPH dinitrophenyl hydrazine, I guess. It is most likely going to give you orange PPT or something. And the other way is using alkaline iodine. So you do need AS knowledge over here. Now, what's going to happen is this iodine is going to form CHI3, I guess, CHI3 and triiodo something. So it's going to form CHI3, which is going to give you yellow PPT. So it reacts with this part, right? So in case of alkaline iodine to react, you need methyl group attached to your carbonyl group, right? That is basically the condition you need for the reaction to take place. The other is DNPH. DNPH will react if there is a carbonyl group attached, ketone or aldehyde. Now, the third one is going to be where both of these are reacting, that is further oxidation is taking place, that is methanoic acid and carboxylic acid are going to be oxidized, right? So how can the oxidation take place? Now, in case of ethane dioic acid, you need a strong oxidizing agent. So that strong oxidizing agent will also oxidize your methanoic acid, right? So that strong oxidizing agent is going to be potassium manganate, hot and acidified. What's going to happen? Under these conditions, your KMnO4 will decolorize from purple to colorless. Now, those are the 6 questions I'm going to solve in this video, and I'm going to make one more video before the exam. So see you in the next one.